Now let's see how we can apply some of the concepts that we've been discussing. Recall that one thing that we can do once we have a polynomial in standard form, meaning that it's in order from highest to lowest degree, is that we can give them names. So degree 0 is constant, degree 1 is linear, and so on. It's interesting to note that as we continue naming these polynomials by degree, that they follow the ordinal numbers in Latin. So degree 8 would be octic, degree 9 is nonic, and degree 10 is decic. All right, so now let's put these ideas into practice. How exactly would we find this information that we need as well as sketch this graph? Well, the first thing that we might want to know is the degree of this polynomial. And it's kind of hard to figure out since this is in factored form. But if we were to multiply everything out, this polynomial would look like 48 x to the 7 minus 240 x to the 6th minus 600 x to the 5th plus 6,000 x to the 4th minus 13,125 x cubed plus 9,375 x squared. Of course, we wouldn't want to have to multiply this out, so there has to be an easier way for us to determine what the leading coefficient is. One thing we could do is we'll notice that if we took just the leading coefficients or leading terms of each factor and multiplied them, we would have 3x squared times x, or x to the 1. And then if we notice this 2x is being raised to, this 2x here is being raised to the 4th power. So we're multiplying by 2x to the 4th power, which if we multiplied it out would be 16x to the 4th. 3 times 1 times 16 is 48. And x squared times x to the 1st times x to the 4th is going to be x to the 5th. Sorry, x to the 7th, because we're adding the powers. So 2 plus 1 is 3 plus 4 is 7. So 48x to the 7th. So that is our leading term. And that leading term is positive. The degree of the polynomial, well, there's a 7 here. So it's a degree 7 polynomial. Concerning the type, we said that the name could possibly be heptic. So how do we find the other bits of information here? Well, the y-intercept, remember that for the y-intercept, we have to make x equal 0. So if we set each of these x values that we have here equal to 0, we should be able to find the y-intercept. So the y-intercept would be 3 times 0 squared times 0 plus 5 times 2 times 0 minus 5. 0 squared is 0, and times multiplied by 3 is 0, so it would be 0 times 0 plus 5 is 5, and 2 minus 0 is 0, minus 5 is negative 5. If we multiply this all out, we end up with 0. So our y-intercept is 0. So this is going to go through the origin. So how do we find out the information that we need about the roots? Well, we have to set each of these factors equal to 0. So let's say that we put 3x squared, we set 3x squared equal to 0. Were we to divide both sides by 3, now x squared equals 0, meaning that x has to equal 0. So one of the roots is going to be x equals 0. X plus 5, we want to set that equal to 0 also. We subtract 5 from both sides of our equation, and x equals negative 5. So x equals negative 5 is another solution or root. And finally, we want to set 2x minus 5 2x minus 5 equal to 0. And if we do that, we add 5 to both sides. So 2x equals 5. Divide both sides by 2, and x equals 5 halves. So let's summarize what we have and see if we can use it. So we know what the roots are. Again, the roots were x equals 0, x equals negative 5, x equals 5 halves. We can look at the multiplicities. For 2x minus 5, it has a multiplicity of 4. For x plus 5, it has a multiplicity of 1. And for x equals 0, it has a multiplicity of 2. We said that the y-intercept was 0, so it's going to go through the origin. The leading term was 48 x to the 7th. That sign of that was positive. The degree of the polynomial was 7, and we call this heptic. So let's talk about the end behavior. If you notice that the degree is an odd number, which means that we would have symmetry with respect to the origin. So we're either going to have a graph that looks like this, where the ends are are either rising and falling, or we're going to have a graph like this, where they're rising and falling in the other direction. So in this case, this is what happens when the leading coefficient is positive, and this is what happens when the leading coefficient is negative. And since our leading coefficient was positive, we know that one end is going to increase as x increases, and the other end is going to decrease as x decreases. We can also put the y-intercept, so we said it's going to cross at the origin, and we can put in our roots. So one root was 0, so we already said it was going to cross at 0. Another root was negative 5, so 1, 2, 3, 4, 5, so negative 5. And another root was 5 halves, which is basically 2.5. So 1, 2, and there it is right here. So now let's look at the multiplicities. For 5 halves, it has a multiplicity of 4, which is even. Even multiplicities cause the polynomial to basically bounce at that point. So if I were to connect it, it's going to go here, and it's going to bounce. The next root is at 0, and 0 has a multiplicity of 2. So it's going to bounce there also. So it's going to hit 0, bounce, and it's going to keep going. The next root is at -5. -5 has a multiplicity of 1, which means that it has to go through that particular point. It's not going to bounce. So we're going to graph it, and this is a basic sketch of what our graph is going to look like, of what our polynomial is going to look like. The first thing that we want to do here is to find the leading coefficient. To find the leading coefficient, we should take the highest degree term from each factor. So this factor only has one term, so it'll be 2. Out of square root of 2 and -x, the highest degree is going to be x. So we're going to multiply that by x, or x to the first power. Same thing here, we're going to multiply by another x to the first power. And same thing here, we're going to multiply by another x to the first power. What we want to note though is this first x that we took actually had a minus sign in front of it. So we're going to put a negative here to make sure that our signs are accurate. So because there are no other numerical factors that we're multiplying here, we're going to have 2. X to the first times x to the first, and let me correct something. This last x actually is being raised to a power of 2. So let's fix that. So x to the first times x to the first times x to the second is x to the fourth. Let's check to make sure the sign is right. So here we have a positive times a negative, which makes that product negative, times another positive still makes a negative product, times another positive value still makes it negative. So our whole expression here is going to have a negative value. So our leading term should be -2x to the fourth power. How do we find the other values? Well, first of all, the leading sign of the leading term is going to be negative. The degree of the polynomial is what we have here. It's 4. And the type is quartic. So we can also find the y-intercept. The y-intercept in this case is going to be, or in all cases, is going to be where x is equal to 0. So we're going to make this 0, make this 0, make this 0, and basically solve for it. So were we to do that, it would be 2 times square root of 2 minus 0 times 0 plus square root of 2 times 0 plus 1 to the second power. So basically that's going to be 2 times square root of 2 times another square root of 2 times 1 squared. These two multiply together just to be 2. So it's 2 times 1 squared is just 1. So that would end up being 4 when we multiply that out. So the y-intercept is at 4. Let's find the roots. So for the roots, we'll set each factor equal to 0. So were we to do that, we would have square root of 2 minus x equals 0. And when we solve for x, that means x is equal to the square root of 2. The next one, x plus radical 2 equals 0. Solving for x, we get x equals negative radical 2. And on the last one, when we solve for x there, x plus 1, we set that equal to 0. So x equals negative 1. So our roots would be at radical 2, at negative radical 2, and at negative 1. Notice that negative 1 has a multiplicity of 2. That negative radical 2 has a multiplicity of 1. And that the other radical 2 is going to have also a multiplicity of 1 because the power is 1. So now if we were to interpret this, let's look at the overall degree. First of all, the degree of the polynomial is even. So there are two things that are going to happen. Either we have both ends are rising, or we're going to have both ends are falling. Both ends are going to rise whenever we have a positive leading coefficient, and both ends are going to fall whenever the leading coefficient is negative. So remember that the leading coefficient here was negative, so that means that both ends should fall. So we're going to have one end falling. So basically, as x goes to negative infinity, our function is going to fall, or it's going to go to negative infinity. As x goes to positive infinity, so as x goes this way, we expect our function to fall. So there's going to be an end here. Let's put in our roots. Actually, let's put in our y-intercept first. Our y-intercept is at 4. And our roots, one of them is at -1. One of them is at negative radical 2, which is about -1.4. So maybe about here. Another one is at positive radical 2, which is about +1.4. So let's look at what's going to happen. When we look at our square roots, square root of 2, it has a multiplicity of 1. Whenever the multiplicity is odd, it's going to pass through the graph. So if we connect everything up, we expect that it's going to go through this particular point, which makes sense because our y-intercept is here. And then it has to hit our other point, which is at -1. But remember that -1 has a multiplicity of 2. So that means that when it's an even multiplicity, we expect that it's going to bounce. And of course, it has to go through our other root, which has a multiplicity of 1, which since it's odd, is going to pass through. So we expect our graph to look something like this. So if we look at the ends again, basically as our x goes to negative infinity, our function is decreasing, or it's falling. So basically, as we get further and further out, our x values decrease, but our y values decrease also. As we go further and further out, as we increase our x values, so as we increase our x values, our function is still falling. So we expect that as x approaches positive infinity, f of x, our function, approaches negative infinity because it's falling.